Okay. I think we can go ahead and get started. So I'm pleased to introduce Dan Kirshbaum. He probably doesn't need an introduction to a lot of you. You might remember him. He was an ASP postdoc here from 2004 to 2006. He got his PhD in atmospheric sciences at the University of Washington in 2004. And from 2006, after NCAR, to 2007, he was a postdoc at Yale. In 2008, he moved to assistant professor at the University of Reading in the UK. And he's been a professor at McGill University in Montreal, Canada since 2011. Dan's research broadly covers mesoscale meteorology with a focus on cumulus convection. He studies various processes controlling cloud formation and evolution from a dynamic thermodynamics perspective, using a combination of atmospheric observations, numerical models of varying complexity, and theory to gain physical insight. That sounds very fancy. I got that right from your website. So. And Dan is visiting M-Cube this week. His last day is tomorrow, and his office is in FL3 3041, if people want to stop by and say hi. And with that, turn it over to Dan.
Hi, everyone. Thanks for the introduction, Hugh. I see a lot of faces from 20 years ago when I was a postdoc here. I haven't come around to your office necessarily and bothered you yet, but there's still time. So yeah, there's still until the end of the day tomorrow. And it's good to be back. So when I was a postdoc here, I was doing my little research and I wasn't totally aware of what was going on in the rest of M-Cube, let alone the rest of NCAR. And work on RKW theory was ongoing, or at least was in the process of getting published. And you know, I wasn't aware of the debate on the topic that was happening at the time. So when I came to revisit it now, I'm sort of regretting that I wasn't paying more attention to it when I was back at NCAR. I kind of felt, yes?
You were still in knickers when we were doing it.
Well, I should have worn more to work than just the knickers, but so I shouldn't have to explain to you what RKW theory is, but maybe some of you could use a primer on it, those who are not RK or W or have worked on it since. And, you know, I'm calling their first article seminal. I meant that to flatter them. And the title was A Theory for Strong, Long-Lived Squall Lines, and as of the 6th of February, there was 1,793 citations. And at times, I may not cover the literature completely because I only read about 1,790 of them. So it's possible that the other three had stuff that I didn't see. But the idea is remarkably simple. As a cloud starts to grow in a conditionally unstable environment, in the absence of shear, there will be equal and opposite vorticity on the two flanks of the cloud, associated with the gradient of vertical velocity across it. Once the cloud starts to produce precipitation, that precipitation will give rise to an evaporative cold pool underneath, and the baroclinicity, horizontal baroclinicity across the cold pool will induce vorticity in this kind of direction, and that will cause the cloud to tilt. Tilt is generally bad for clouds. It prevents them from accessing the instability as efficiently in the environment. So this would weaken the intensity of a cloud relative to an upright cloud. Now, if a cloud forms in the absence of precipitation and a shear flow, it will tilt in a way that is consistent with the environmental shear. And in this case, the environmental shear has a tilt in this direction. But in the case where the cloud produces precipitation, the environmental shear can balance the cold pool vorticity to give an upright updraft, and that's sort of the idea of the theory. So it's about a balance. The theory involves a balance between cold pool vorticity and low-level vertical shear that will maximize system strength and longevity for a given environmental state. Mathematically, they kind of performed a control volume analysis. This is a picture from Arkowski and Richardson that kind of gives a little bit of insight into this control volume. The condition for an upright updraft is that delta U, which is some wind difference over some layer, is equal to C, where C is the 2 times minus the integrated buoyancy within the cold pool over the cold pool depth. Now, delta U is the shear over some layer going from the surface up to a height d, and d is a sort of hypothetical height at which the vertical vorticity flux is 0, integrated horizontally across the control volume. That is the equivalent of saying there's an upright updraft. So that's the theory. And there was a lot of pushback on it. This wasn't just immediately accepted. There were a few studies that sort of challenged the theory. Lafore and Moncrief were thinking that it neglects the larger scale kind of gravity wave circulation of the whole squall-line system, including trailing stratiform regions. Zhu and Moncrief thought of it more as a global flow force balance, as they called it. Again, thinking larger in scale than just what happens along the leading edge of the cold pool. Coniglio and Stensrud et al. 2005, pointed out that the theory doesn't seem to explain warm season progressive derechos, where most of them were found to be suboptimal in their analysis in, I think, numerical simulations. And they strongly felt that upper level shear was also important, and the theory neglected that. So Weisman and Rotunno came back in 2004. I don't think Kay was involved in this one. They showed, using a 2D analytical model and 3D squall-line circulations, that supported their original contentions, even looking outside the original parameter space that they had developed the theory. Bryan et al. Did a multi-model assessment of RKW theory, where they argued that, yes, according to their analysis, the theory did explain the system tilts and intensities. I would say that probably the most ferocious criticism came from this paper in Stensrud et al. 2005. But as far as I'm concerned, RKW theory is just part of mesoscale meteorology now, and it's not really, the debate is kind of over for the large part. I'm looking to reopen it because, I want more controversy. But the theory needs to be applied in a proper context. This doesn't explain everything about squall lines. All it explains is the tilt of the leading updraft ahead of the cold pool. So there are factors that affect deep convection that are not part of the theory, like the environmental instability, and that's kind of a limiting effect. You can't, if the instability is weak, the convection cannot be that strong, and RKW theory can't make it stronger than the instability allows it to be. It can't explain everything, but that's not a problem. I mean, there are no theories that explain everything at the moment, so it's still a viable theory. But quoting Weisman and Rotunno in 2004, they said an important step in judging the success of the theory is whether it can be successfully applied to describe real-world squall-line behavior. And that was my mission here, is to look at real-world squall lines and see how well RKW theory explains it. Now, if anyone knows of any work that used observations to verify RKW theory, I would be very appreciative if you would share that with me, because I was, as I said, didn't read all of the papers, and I wasn't able to find one that did something similar to what I'm doing here today. There have been sort of case-by-case analyses, or maybe a few cases at a time, but never something that involved tens of squall lines. Like I said, though, please let me know. In Vortex 2, in that field campaign, they would launch frequent radiosondes as the squall line was approaching, and so they did have good data of profiling data across the squall line, and at least for one case, they found that RKW theory did explain the reverse system tilt of a very strong squall line. Now, what would be the goal, if we wanted to evaluate this theory observationally, what would it look like? Well, we want to characterize C and delta U, again, the cold pull intensity and the vertical shear that might balance that. We'd also want to evaluate the tilt of the system in the vertical, and then how the intensity, the squall line intensity and evolution, we want to see how that relates to these parameters. But this requires observations that are not routinely available. One, and probably the hardest thing, is to have high frequency, on the order of 5-minute or less, buoyancy profiles across the squall line, or thermodynamic profiles, same thing. This will allow to evaluate C, and also the pre-squall line environmental state. We also would want high frequency, but maybe less high frequency wind profiles to get a good measure of the shear of the ambient flow ahead of the squall line, and then some way of measuring tilt. And that's not that easy to measure, because even if you want to use radar to measure system tilt, precipitation, if you want to use Doppler winds, they're very affected by precipitation and the fall speeds of precipitation. So you don't necessarily see kind of the system relative flow, even from like a dual Doppler analysis. You can maybe see it. Precipitation is generally very bad for measuring the tilt, and these are precipitating systems, so that's a challenge in general. But these types of observations are not routinely available in most places. One additional issue that kind of just stands out in the literature is the definition of D, the top of the control volume. How to set it. This is something that if you have a squall line and a 3D gridded data telling you where the squall line is, you could get a very accurate measure of where D should be. Again, D is where the vorticity flux in the vertical is equal to 0. That's kind of near the top of the updraft. And people have chosen different heights for this layer to measure the shear. Weisman and Rotunno chose 5 kilometers, because that tends to be about twice, that's around twice the typical cold pool depth. Chen et al. Chose 3 kilometers. A variety of papers have chosen the cold pool depth H. And whether the theory holds totally depends on how you choose D. So it's a hard, that is, I would say, one of the most difficult aspects of observationally verifying it, where to choose this height. Now, my observational analysis is going to use the ARMS Southern Great Plains Observatory. It's going to use data from Lamont, Oklahoma, and surroundings. I think most of you probably know what ARM is. It's the Atmospheric Radiation Measurement Program run by the Department of Energy. It's a continuously running observational supersite, and, as ARM claims, the world's largest and most extensive climate research facility. Some relevant observations that made this an attractive place to evaluate the theory are the presence of Doppler Lidar, ARRI, which is a passive infrared radiation instrument, sounding launches every 3 to 6 hours. There's a surface mesonet shown here. I'm actually not going to use that. When I first made this slide, I was using it, but then I found a better way to deal with one aspect of the analysis. And there's also a radar nearby, the Vance Air Force Base radar shown here in blue. So we have a lot of observations, and the objective here is to use these observations to estimate the various physical quantities implicated in RKW theory, and then use these estimates to critically evaluate the theory. To find cases, I'm choosing an 11-year period from 2013 to 2023, and this is ongoing. The next squall line in Oklahoma, that gets added to this data set. It's a manual process to identify squall lines. I could download all the radar for 11 years, and once I've basically, bought petabytes of storage, then I could maybe automatically find these cases. But what I chose to do is just run through the Storm Prediction Center, the NOAA Storm Prediction Center's severe weather reports, kind of run through the whole year and find cases, any case where there's severe weather reports in this region. And then I went to radar composites and looked at just the radar animations of whatever convection was happening, and made a subjective determination if the system is intense and quasi-linear. In that case, I would consider it for further analysis. And this led to 46 quasi-linear mesoscale convective systems. I'm not going to call them squall lines. Some of them don't look like traditional squall lines, but it turns out it's actually hard to find cases where you have all the data you need. So you have to be a little bit flexible about what cases you're going to admit. And it turns out in the end, I'll only have 11 cases that I'm going to analyze in detail. This is what the 11 cases look like from the VAFB radar. There's a lot of variability among them, but what you see in each case is some kind of organized convection. Now in this case, it's actually a squall line that's going to develop right over the Southern Great Plains facility, which is probably not the best to test the theory, but again, I was trying to be flexible with my cases. Every case has a noticeable cold pool given by like a radar fine line ahead of the squall line. In this case, it was actually a convergence line on which the squall line developed, and you can kind of see that here. So every case had this cold pool kind of ahead of the squall line, and the time that I'm showing here is the time at which the cold pool crossed the SGP facility, which is given by the red dot here. In a few cases, the squall line was actually already decaying by the time the cold pool came through. Like this case here, you can see that this case, there was no rain actually associated with the squall line because the cold pool just fell, the squall line fell apart before it actually reached the station. But even if you have a squall line that's actively decaying, you can still apply RKW theory because it's supposed to predict the evolution of squall lines. So I'm going to take the first case shown here, case 1 of 11. This was 16th August 2013. You can clearly see the fine line. This is the cold pool boundary ahead of the squall line. It's 2 o'clock UTC, so this is in the early morning hours, and this is when most of the squall lines happen. What I do with the, here's an animation of the squall line as it comes through. Now, the angle of this black line is a estimate of the orientation of the cold pool. It's supposed to be aligned with the cold pool as it passes through, and you can see there's uncertainty there. I give it a 10-degree uncertainty. I also estimate the time at which the cold pool comes through, and I estimate using transects normal to in the squall line normal direction to estimate the cold pool speed, which is 16 plus or minus 2 meters per second in this case. The big data set that's going to help to test this theory is the AIRI and the atmospheric emit, I don't even remember what it stands for, but it's a passive infrared device used to retrieve temperature and water vapor profiles at 5 minutes frequency. The problem is it doesn't function during precipitation. So I want to use this to look at the buoyancy inside the cold pool to help test the theory, but once there's precipitation, the hatch closes on the instrument and it no longer takes data. So there's a sampling bias here in that I need squall lines where the cold pool's running ahead of the precipitation because I need that time period to measure the buoyancy in between before the rain starts. The estimation, the retrieval used is called TROPO-E. It was developed by Dave Turner, who's a collaborator on this work. It has 55, I won't talk about the radiative transfer model, but I will say that there's 55 stretch levels from the surface to 17 kilometers. The resolution's very high near the ground, and then it gets worse aloft. And this is case 1, showing the theta V perturbation relative to the 30 minutes before the cold pool came through. This is centered on the cold pool crossing. You see the cold air following the cold pool, as you would expect, possibly some waves ahead, maybe associated with a bore. And how I estimate C is I take the 30 minutes before the cold pool comes through, and I average that as the environmental state, and then I compare, then I take the perturbation relative to that environmental state, and that gives this profile in the post-frontal, so post-cold pool period shown here. So we see this negative buoyancy extending up to a height of about 1.5 kilometers. This is H, the top of the cold pool, buoyancy goes positive above there, so we can integrate this vertically to get C. We can also get errors. There's information provided on the posterior covariance matrix, so we're able to get an error estimate, although these errors are most likely underestimated because there's no error in the assumed in the radiative transfer model. Now, just to verify the area, I mean, you always want to be sure that what you're looking at is good data. And I verified it against the surface meteorology data, mostly co-located. So the surface meteorology is the MET, and the area is MET in black, and the area is in blue. These are three cases. The cold pool comes through, the air cools down. And what I did was I only accepted cases or admitted cases when the change in theta V between the first 30 minutes and between the pre-crossing 30 minutes and the post-crossing is less than 30% of the value of the Met station. So I'm kind of admitting a 30% error, which was needed because the area is not perfect. It has a lot of trouble with rapidly changing temperature because it uses a first guess based on the previous temperature measurement, and sometimes it has trouble when the temperature changes 10 degrees within a span of 5 minutes. Now, to estimate delta U, I use this orientation that I had estimated before, and I look at the component of the wind normal to the squall line, normal to this black line, in the direction of squall line motion. And where do I get my wind profile? I use an observed sounding if it's less than 3 hours before the squall line crossed, or less before the cold pool crossed. ARM conducts 6-hour SON launches at the Lamont SGP site. So most cases I have a sounding that does satisfy that criterion. But if that's unavailable, in one case I chose an Oklahoma City sounding there was just no Lamont sounding at the time I needed, but there was an Oklahoma City sounding. Or I chose a RAP model sounding in 3 cases over the 1-hour period before the crossing. Vn is the wind component in the direction of cold pool motion, so it's in the minus y direction here. Okay, so here's a profile from case 1. The U profile is shown in blue, V profile in red, and then the normal profile is shown in black. Now, as I mentioned before, the height of D, the layer over which to estimate the shear is very uncertain. So I chose 4 different metrics. One is taking the difference between the top of the cold pool, which I get from the ARI, and the minimum surface normal wind over the lowest 500 meters. And if I do that, I get a 5 meter per second delta U. If I go up to twice the cold pool depth, which, at least it's flow dependent, it may, the justification for looking at twice the cold pool depth is that maybe there's low level convergence all the way to the top of the cold pool, and then you need divergence aloft for the updraft to go back to 0. And those 2 layers maybe are related, have a similar depth. If I use 5 kilometers like Weisman and Rotunno did, I get 13.4 meters per second. 5 kilometers is up here. And another measure that I'm using, which is going to turn out to be the best measure, is just if I take the maximum value over this 2H layer minus the minimum value over this 2H layer. Now, it's hard to justify that. You might say it's the maximum shear in the in the layer of the the layer near the cold pool that could possibly be available to rectify this updraft, prevent it from tilting backward against over the cold pool. So that's my reasoning, but I probably need a better justification. The errors on this are determined by varying the cold pool orientation. So that orientation line, I said there was a plus or minus 10 degree sort of uncertainty in there. Doppler Lidar is the next measurement that I'm going to include. So what I'm going to use the Doppler Lidar for is to measure the tilt below cloud base, because Lidars can't see above the PBL top or cloud base. It's a vertically staring Lidar, temporal resolution of 3 seconds, vertical resolution of 30 meters. Data is masked when the signal to noise ratio is very low. Here is a few contours of the Doppler Lidar observed updraft relative to the ARRI data, and you see it's kind of well aligned with the leading edge of the cold pool. Okay, so how do we estimate the tilt of the subcloud updraft? Now you might be saying, well, I don't care about the subcloud updraft. I want the system tilt. Well, just bear with me, we'll get there. But subcloud updraft is something you can measure with LiDAR, so I thought it was worth doing. I kind of use a object-based method where I use thresholds on the vertical velocity to identify different updraft objects for different vertical velocity thresholds. And then I look at the centroid of W at each vertical level and kind of get these dotted profiles that you can kind of see here. And then I use a linear regression to get just a single line that is representative of the tilt. So you can see that the tilt for different values of W threshold can vary by a significant amount, but this is a fairly upright updraft with pretty weak tilts. Now, how do we estimate system intensity? Again, we want to know C over delta U. I've described how we're going to do that. We need the system tilt. I've described how we're going to at least do that in the subcloud layer. Now we want an estimate of system intensity. So what I've done is a bit convoluted, so I'll just get to the point. In the normal direction to the squall line, I find the leading edge of the squall line and I track it in a 30 by 30 kilometer box. And you can see in this animation how that looks. So it only tracks it within this region. You don't want to track it for too far a distance because we only have data at this one location. We can't talk about the entire squall line, particularly this one because it's not really a squall line. It's like a bow echo, but it's kind of linear in the segment that passes through the SGP. And I'm going to track that with time and then do statistics within that box as the squall line comes through. So here it is. The box locks into it, and then it tracks it as it moves across and through the SGP. This required some averaging across the box and a variety of things to get a robust kind of tracking of the squall line. And I analyzed quantities over the 1 hour centered on cold pool crossing. Again, we only have data. All of this analysis is right when the cold pool crosses. So we don't want to try to explain things that may no longer be relevant to those measurements. There are three quantities that I'll use to estimate system intensity and evolution. One is the fraction of grid points exceeding 40 dBz within this box. This is kind of saying how full the box is with strong convection, or exceeding 40 dBz at least. Another measure is the time tendency, again using a linear regression of how that measure, which I call F40 dBz, how that varies over this 1 hour period, and then the mean maximum reflectivity over the hour-long period. I think I mentioned the slope of this linear trend, which is, yeah, I already said that. So here's one case. If we look at this is still case one. What we see is the fraction of the box that is filled with 40 dBz echoes is around 0.2, regardless of the orientation that's assumed for the system. But you can see that the trend differs based on what you assume to be the squall line orientation or how you estimate that. So it just shows that there's some, the error is significant in our estimates. If you take that error into account, you get variations in the result. Okay, so let's get to the results. This is C over delta U versus subcloud updraft tilt. Look using different measures of the height at which the shear layer is being calculated. Now, some of this looks really ugly, so you might want to just look away at some of these results. But this is if I use the cold pool depth, if I use the shear layer equal to the cold pool depth. This is if I use the shear layer equal to twice the cold pool depth, 5 kilometers, and then the maximum minus the minimum. Now, what we expect to see is that as C over delta U increases, then the system becomes increasingly cold pool dominated and should have more of a tilt. Because tilt is positive when it's reversed, when it's the way I've defined it. It's when it's going back over the cold pool, when it's up shear, that's a positive value. So the only two that give meaningful correlations here, what we should see is the tilt should become negative when C over delta U crosses 1. And that does seem to occur for some, at least in some of these, and then it gets more and more positive as C over delta U increases from 1. It should be around 0 when C over delta U is equal to 1. And if we choose a 5 kilometer depth for the shear layer, it looks pretty good. We get a correlation of 0.44. The significance, we'd say this is only significant at the 83% confidence interval. So not great, but this is only 11 cases. If I use the max minus the min, the U Vn over this layer, then I get a slightly higher correlation as shown here. In general, the C over delta U values are much smaller because we're using sort of the maximum delta U that we can get. So it's a decent relationship, C over U versus updraft tilt. That's promising. It gets better here where I look at C over delta U versus the evolution. This is the change in the fraction of 40 dBz as a function of time over this hour period, again using linear regression to estimate that amid the noisy data. So if I choose the D equal to cold pool depth, you see there are fewer points here. That's because C over delta U there are huge values of C over delta U that you can't see on this plot. And these regression lines that I'm showing include all the data, not just the data shown in the plot. But for purposes of illustration, I cut off C over delta U at 5. If I choose D equal to 2H, so twice the cold pool depth for the shear layer, then we see a negative sensitivity. And that's what we should see, because as C over delta U increases from 1, we should see more tilt and faster decay of the system, according to the theory. So we are seeing that here for D equals 2H. We see it's a little more scattered for D equals 5 kilometers, not a great relationship. And then it looks really good for choosing the maximum minus the minimum, Vn over 2 times the cold pool depth, where we're now well into statistical significance territory and a very strong negative correlation. Intensity is a similar story, with some small differences. We see that when D is equal to 2H, there's a negative trend, but it's not very strong. If we choose D equal 5 kilometers, we do get a nice trend with a correlation minus 0.58 and significance, higher significance. And then it also looks good for the maximum minus the minimum. So that's promising. Until we then look at the maximum radar reflectivity over this period. And what we see is it actually, in most cases, seems to increase with C over delta U, not decrease. But none of this is even close. Maybe this D equals 2H is close, is a strong correlation, but this is not what the theory is predicting. The theory should predict that we get weaker intensity for larger C over delta U for all else equal. All else is not equal, though. That's the issue here. So we don't get a good relationship between the maximum radar reflectivity and C over delta U. We can also just jump right over C over delta U and compare the tilt to the intensity, because the theory, C over delta U is just a predictor of the tilt, and if the tilt if it's upright, then we expect the highest intensity. So we should see an even stronger relationship between the tilt and the intensity than between C over delta U and the intensity. And this is showing the 3 different measures this is the system evolution. This is one measure of intensity, the fraction of 40 dBz, and then this is the maximum dBz. And it doesn't look very good except for this one. We should have a negative slope here. Again, larger tilt, weaker intensity. It's not a strong correlation here, but it is of the sign that we would expect. Here it's a positive correlation, which doesn't agree with the theory. So that's kind of concerning. We've kind of taken out the middleman, C over delta U, or I should say, yeah, there's no middleman. But the idea is tilt should relate stronger to intensity and evolution than C over delta U does, because C over delta U is just a predictor of tilt. So what's going on here? The problem is that using the subcloud tilt is a problem. Here's one case that shows a bore propagating ahead of the cold pool. The cold pool's coming in late, but from the radar, I saw a fine line well ahead of the cold pool, and this is associated with a bore. These are mostly nighttime squall lines, so we do have bores in some of them. And you see these really strong updrafts. Now, the area's not really reliable above cloud base, but usually the cold pool, cloud base is near the top of the cold pool, so that's not that's not a huge problem. So I wouldn't trust the data aloft that much. But you see that Doppler is showing updrafts, multiple updrafts, well before the cold pool comes in, and there's no guarantee that the way I'm identifying the updrafts or the cold pool, the fine line boundary will correspond to the updraft that is aligned with the cold pool. It might be a bore updraft. So there's a kind of uncertainty in just choosing which updraft to measure. It also complicates the definition. How are we going to define the environment ahead of the squall line? If I consider this to be the updraft, then the environment's much warmer than if I consider this to be the updraft. So the environmental state is very sensitive to sort of where you choose that updraft to be. So this is all adding a lot more uncertainty that I hadn't really taken into account before. So another, probably the biggest problem, is that the LiDAR can only see to cloud base or the PBL top, whichever is lower. And when the cold pool comes through, cloud base tends to sink, like cloud base really lowers toward the ground. And so a lot of these updrafts kind of have this slope that's downward slope as the cold pool comes in. That is going to sort of cut off part of the updraft, and it's going to make our estimate more upright than it should be. So you can kind of see that here. We see these centroid lines that are going more negative, but then they sort of come back and become more upright here over this area where the top of the updraft, or the updraft probably extends into the cloud layer, but we're just not seeing it with the LiDAR. So what we probably need to do is to estimate the tilt of the whole system. So we have to go into the cloud layer. The subcloud tilt isn't going to be enough. So maybe in the cloud layer, we have an updraft that might look something like this. Maybe it has a reverse tilt, but it could be different when you look over that whole feature than just the subcloud part of it. So how are we going to do that? Well, at the ARM site, they have a vertically profiling cloud radar. This works in some cases. In this case, it works really well. Shows this updraft extending well into the cloud layer. It looks like a slab updraft. There's some convection out ahead. I would imagine this is associated with gravity waves aloft that's initiating these clouds, but the updraft in the subcloud layer connects to the cloud layer, and you see this is something that you could actually measure the tilt. But I can only do this in 4 cases because in the other 7 cases, the rain is just totally obliterating the updraft. The fall speed of the rain, you can't see the updraft in the cloud layer because it's overwhelmed. And also, it's kind of hard to develop an automatic algorithm because the KZR, as it's called, Ka-band zenith cloud radar, its signals are pretty weak near cloud base. So like you see this area, this is a low signal to noise ratio. There's probably a strong updraft in here. It just doesn't see it because there isn't a lot of liquid water in the cloud yet. So it's going to be harder to measure the updraft tilt from when we combine these 2 instruments, but we can have a go at it. This line that I drew is totally subjective, but it measures a system tilt of 76 degrees from the vertical. You could say that I should originate this line from the surface, and maybe that's something I'll do in the future, but this was just kind of a rough estimate, and it's a manual one. Now, if I compare the subcloud tilt to the system tilt, they don't agree very well. And you can kind of see that here. Like the subcloud tilt looks almost, it's quite upright, but the system tilt is it's leaning over the cold pool. And so the system tilt is always greater than the subcloud tilt, as we see. Now, when I measure the system tilt, I'm really just following the cloud layer updraft as high as I can see it. Like, once I can't see it anymore, so I measure the tilt of the part of the updraft that I can see. But we see that there's a big difference between the subcloud and the system tilt. Okay, so this is a result I already showed. This is C over delta U versus the subcloud tilt. We saw the best result for this case using the maximum shear available in the cloud layer, or in the 2 times the cold pool depth layer. Now this is the system tilt. I only have 4 cases. And so I'm looking at C over delta U versus the system tilt. And again, we get positive correlations as we would expect to see. We expect larger tilts for larger C over delta U. But again, this maximum minus minimum just like matches it so well for these cases. So let's look at intensity. System tilt against intensity. We saw the subcloud tilt looked really bad, except for the evolution. There was a correlation, but it wasn't very strong. Now, when we look at the system tilt, we see that the evolution shows a clear there's a decay as C over delta U, or as the tilt increases. That's what we expect. F40 dBz is decreasing with the system tilt, but the maximum reflectivity is still not. The maximum reflectivity is still kind of doing its own thing. What's going on there? Short answer is, if you were to include CAPE as one of the control variables for the maximum reflectivity, then you see a good correlation between the system, the maximum dBz and CAPE. So it looks like the sort of maximum intensity of the squall line is determined by CAPE, but the evolution and the sort of how packed the tracking box is with large echoes is more explained by the system tilt. Okay, so I would say this work is not quite complete because now I talked to Dave Turner and he told me a bunch of things that I should do to improve my area analysis. But from what I'm seeing, RKW theory holds up under scrutiny over 11 quasi-linear mesoscale convective systems in the SGP region. C over delta U, when appropriately chosen, explains the squall line tilt, intensity, and evolution. C over delta U explains not just the system tilt, but the subcloud tilt, because it correlates well with both of them. It's just the subcloud tilt doesn't relate well to the measures of the overall squall line system. But all of these quantities must be calculated carefully. And some of them, I sort of tried something and it worked really well, and I'm still trying to justify what I did. And that's this maximum minus minimum normal wind. And this seemed to work the best. It yielded the strongest correlations with subcloud and system tilt, system evolution, and intensity. I think the fraction of 40 dBz echoes is a better measure of the RKW theory than the maximum reflectivity in the tracking box, because what the theory is trying to predict is the strength of the updraft along the leading edge, the tilt of the updraft, and hence the strength of the updraft along the leading edge. So what that's kind of telling you is how solid the convection will be along the leading line. And so more solid convection should give you a larger value fraction of 40 dBz. dBz max correlated better with CAPE, though, which makes sense because CAPE is telling you kind of what the potential intensity of the system can be. And the system tilt seems to be a better measure of tilt than the subcloud tilt, which probably you would have told me at the very beginning, but I still went through the exercise of kind of confirming that. So for future work, now that I think the system tilt is where it's at, there were a lot of cases where I did not have good Doppler Lidar data, where precipitation or cloud-based was kind of cutting right into the updraft and I couldn't see it well. Well, now those cases that I had abandoned because I didn't have good measures of subcloud tilt, I can now look back at the cloud radar and see if maybe I can measure the system tilt, so I might be able to increase the number of cases. I'd like to develop an automated tilt calculation. Obviously, we want to automate things in science, so subjectivity is kind of taken out of it. I haven't done that yet, but hopefully soon. I'm thinking of maybe there are some idealized squall-line simulations that I can run or if you want to collaborate, that we can run to test, to maybe understand, or maybe this maximum normal wind minus minimum is just a fluke and it looks good, but not for any good reason. And so I'd like to play with some shear profiles that have a lot of variability in the wind in low levels and sort of see which measure provides the best, correlates best with the system tilt intensity and stuff like that. And yeah, there's other ways of estimating delta U. We do have Lidar wind profilers, radar wind profilers, although neither of them, I'm not sure if they'll work, but we can always improve the way these things are calculated. That's the point. So with that, I'm done. Thank you very much.
Thank you. I imagine there's going to be some questions here. All right, we'll go first with the W and RKW.
I object.
Strenuously.
No. I feel your pain with all of this, and I appreciate the effort you went to this. I just wanted to perhaps explain the difference in the D and the H values and the fact that, for example, we chose in the 2004 paper 5 kilometers. And that was really aimed at correlating with different squall-line metrics. For example, things like the total precipitation over a 6-hour period as the strength and so forth. And so I think it depends on the kinds of metrics you're using to measure intensity. And the 5 kilometers also accounted for other aspects like deeper shear and whatever. And so, I think it's consistent. I don't see any problem with your Vmax minus min. That seemed as good as anything. So I would pursue that. But
Good.
Yep.
Thanks.
Along those lines, based on that question, I will point out George on the Slido said, not a question, but a comment, D depends on the shape of the wind profile, and then referring to his paper with Rich in 2014.
Okay.
So we'll go with Peggy next.
Yeah, can you hear me? I have a question about the definition of tilt, because the maximum vertical velocity, all that tells you is that the air above the same point is going up. But if, say, you had a sine wave or something like that, you're not describing air going from the surface all the way through. You're just seeing where the vertical velocity is maximum. And if you really want to measure the tilt of the updraft, you need to take the ratio of the horizontal velocity and the vertical velocity in the coordinate system of the storm. And I think what you do when you have a very strongly tilted maximum like that, it might very well be along, reflect that ratio of W versus U, and maybe that's why your system relationship looks better with your system tilt.
Okay. Yeah, thanks.
And the second, just a comment, in GATE, we also had a few squall lines with lots and lots of measurements. It might be interesting in looking at those as well.
Okay.
A totally different environment.
So a possible, physical explanation for your Vmax minus Vmin, I think is because you're in the nocturnal environment in Oklahoma, and often you have low-level jets, and at the top of the peak of the low-level jets, usually where you have your peak buoyancy. So I'm wondering if you're looking, at the near surface winds, that air may not even be buoyant or able to really realize that buoyancy. And I guess kind of along those lines, I think that's something just in general, like when I've also tried to apply RKW theory to nocturnal systems, so I definitely can appreciate the challenge behind, or coming along with doing that. But even in numerical model simulations is difficult. But I think also looking at the near surface stratification in general and how that applies to the theory of the cold pool strength is something to think about.
Yeah, thanks. Some of the cold pools, to the extent that we can trust the area retrievals, some of the cold pools were elevated above the surface. And it's kind of, this measure is kind of, isn't so sensitive to what's happening right at the surface or in the nocturnal boundary layer. So I think it's helping in that way. I already tried to sort of account for that by looking at the lowest normal wind in the lowest 500 meters, just kind of based on the sort of bulk Richardson number type of analysis of Wilhelmsen. Just kidding. Come on. Okay, so of Weisman and Klemp. So yeah, I mean, I totally agree that that in the nocturnal boundary layer, starting your analysis at the surface is not well justified. So yeah, but thanks for, there were a lot of low-level jets, and there's a ton of shear at low levels in most of these cases. So some of that projects into the squall-line normal direction, and that's probably one of the main reasons that these squall lines are so happy at night.
So I'm wondering to what extent your analysis is reliant on getting the correct structure from the ARI, because the ARIs tend to sort of come up with structures that are aligned with climatological means rather than being truly range-resolved observations.
Well, I'm not sure. I mean, yeah, you're right that the climatology is used, the covariance and the climatology is used to relate lower and upper level. But at lower level, you know, my sense is the ARI is pretty reliable. And except that when squall lines come through, there's such a dramatic change in temperature that the ARI may struggle with its first guess and not converge on the right answer. And that did happen in some cases. But in cases where and I can show you the ARI from all 11 cases, and sometimes aloft it looks terrible. But the cold pool looks realistic, you know, at lower levels, and that's where I'm doing the buoyancy calculation. So it's also, ARI also struggles with clouds. When there's significant liquid water content, it just tries to fill in the gaps with climatology or with the sounding data. So at upper levels, the algorithm is trying to fit it to the interpolated sounding as well as the climatology. It's like it's you know, one of these variational methods, I think, that takes into account, you know, there's multiple data sources and they have their errors, but Dave Turner says that they're more trying to match the interpolated sounding. Now, the interpolated sounding has problems because if you have a sounding 6 hours before a squall line, a sounding 6 hours after a squall line, or 3 hours before and after, it's going to see a linear decrease, when in reality, it was probably like the temperature didn't change much and then fell right down. But that's also happening at lower levels, and I would say the ARI is very uncertain in general. So, you know, I just tried to give it a go, and I'm using their error covariance matrix to try to estimate that error, but there's other sources of error that probably are underestimated and could lead to some problems in certain cases.
Did you try checking it against the Raman Lidar retrievals? Because I think that operates right at the central facility as well.
It does, and I haven't, but that's a good idea, and actually it's something I had thought about doing. But I will say, Raman Lidar doesn't do temperature. Yeah. To my knowledge.
Rotational Raman.
Okay, well, I don't think at the SGP, the Raman Lidar that I have was actually taking temperature from the ARI. It didn't have its own temperature measurement, but maybe that's changed. Maybe the retrievals have changed, but I don't know.
At least 15, 10 years.
Okay, well.
Yeah, talk with Dave because he will know.
Okay, I'll trust you because I am not the expert on this.
Temperature is easier with Raman than water vapor.
Okay.
So.
Yeah, I know Raman can do temperature. When I look at the data, I don't, when I download the files, it doesn't seem to be available. But that's my problem, apparently. So, good. Thanks for the suggestion. I will kind of look at Raman Lidar. Although I will say that ARI has been, you know, evaluated. Like those retrievals have been evaluated before. This is not the first time that someone's doing it. I was just trying to verify them because of the cold pool issue. So, you know, Dave Turner's written numerous papers about how well they verify against other data sources. And I didn't necessarily want to plunge into that in great detail, but I was kind of hoping to rely on those verification tests. But I agree that it would help to have more verification of the chosen cases.
Okay, yeah, Rich.
So I remember well back in the 90s, the anti-RKW reactions. And some of the papers were, well, this doesn't work based on data. Some of the papers were, well, this doesn't work and my model shows upper level shear is important or something else is important. Have you considered the other theories that might explain any of this?
No. I mean, I wanted to
Because
focus
my view, they're not testable, a lot of these things that people are saying.
the other theories.
Yeah.
Yeah, I mean, I didn't have a clear idea of how to go about that. And I'm not sure if the observations would really allow me to do that.
What are all those other theories?
Well, I would say that the Zhu and Moncrief, like I found that to be kind of inscrutable. Like I wasn't sure what to make of that. I decided that I wasn't going to kind of spend hours and hours trying to understand those papers because I was just going to focus on RKW theory. But I thought like the Coniglio and Stensrud type of arguments were that upper level shear is important, but that there wasn't really a theory behind it. It was just sort of like, well, RKW bad, upper level shear good. And so that's not something that I can really do much with. Maybe I'm probably wrong. I mean, there probably are some clearer theories, and I would like to know them to help inform this work. I mean, theory implies that you have a mathematical model for something, and Zhu and Moncrief have one, but I didn't get the sense that I could actually use observations to test that. Again, because theirs involves the whole squall-line system, which is poorly observed, at least by the instruments I'm using, once it starts raining.
It's in steady state.
It's okay. Well, that too.
Let's go with one more comment.
Okay. Yeah, one pro-RKW comment and one anti-RKW comment. First, there's an article in a recent Physics Today about a study that some people did where there was actually, quote unquote, so much shear that the squall lines that they simulated actually went at an angle to the shear so that they could get the optimum value from an RKW point of view, which is kind of interesting. Mm-hmm. The second thing is referring back to GATE. It's the 50th anniversary, and I just came back from a meeting about that. The majority of the convective lines, and they weren't as severe in GATE, were actually parallel to the low-level shear. And there is no theory to explain those yet. You can compare them maybe to horizontal roll vortices. So there probably are classes of non-RKW lines which we don't understand yet.
Yeah, I mean, there's also the fact that large-scale forcing can produce a squall line on its own, and if the cold pool doesn't destroy it, then it can be maintained. A front could produce a squall line that can last a certain amount of time. So I think there's mechanisms out there with larger scale forcing that can produce linearly oriented convection. I mean, about the shear parallel thing, yeah. I mean, I don't think the theory, the linear theory of how convection organizes with shear would apply to a squall line, because once it goes nonlinear, the theory is basically useless. But that is an interesting point, and yeah, the squall lines that are organized by the upper levels are just. We tried actually to sort of account for that at some point by saying which squall lines were aligned with fronts, and as analyzed by the WPC surface archive, and which were sort of ahead of fronts and which were along warm fronts, and we were trying to see if RKW theory held better for the squall lines that are not associated with large-scale forcing, but we just don't have enough data to do something meaningful like that. So that might be, if we could get a larger data set, then we might find that the outliers are a certain type in a certain synoptic environment.
Okay, well, let's thank Dan one last time, and then we'll move the discussion out to there.